Hey, so in this screencast, I want to talk to you about nuclear power. And look, I'm going to be right up front about this. I'm a big, big advocate of nuclear power. In my opinion, and in the opinion of many people, it is the one thing that could save us from the calamity that's befalls us, right? I mean, like right now, fossil fuels are destroying our atmosphere, destroying many ecosystems, and they're going to run out and destroy our economy and our society as well. They're not good for us. And nuclear power could be our salvation. We know how to do it, but most people are afraid of it. So I think they're afraid of it because of their ignorance. I don't want you to be ignorant, so let's learn about nuclear power. So, nuclear power basically releases nuclear potential energy as opposed to chemical potential energy that's released from conventional like hydrocarbon and coal. Um, but the process is called nuclear fission. Fission means to split the atom. So how do you split the atom? So keep in mind that the nucleons that make up a nucleus are two. There are protons and there are neutrons. In this diagram, the red are protons that have a positive charge, and the bluish ones are the neutrons, which have a neutral charge and serve to sort of glue the nucleus together. And it turns out if you have a very large, unstable nucleus, like, say, uranium, it is possible that if it's hit with a neutron at the right speed, that neutron will cause this large nucleus to split in two. And we call that process fissioning. And what happens is the resulting fission products, or fission fragments as they're called, have less total energy in them. And so that release of energy is given off. Now, that's the basic process we have, right? Taking a big atom, splitting with a neutron, turning it into smaller atoms, and since there's less energy in the smaller atoms there was when they were put together the big one, it releases energy, and I'm talking a lot of energy. Now, these fission fragments are products. The idea is they have less nuclear potential energy, and so this is a curve that don't worry, you don't have to know this curve, but it is worth looking at. This is what we call the curve of binding energy. So here's uranium out here, right? This is how this axis here is energy, and this is how many nucleons are in the nucleus. So what happens if I split a uranium 238? It ends up each of the pieces ends up down here. So what happens is every single proton and neutron now has significantly less energy in it here than it had when it was up here. So that energy gets converted to heat, and you can use that to do good things like run a city, or bad things like blow up a city. Now, interestingly, the sun goes on the opposite end of things. So the sun takes hydrogen, which is here, and converts it into helium, which is here. So you can see there's this very significant diminishment in the nuclear potential energy, and so there's a tremendous release of energy by the sun, which, by the way, this is how hydrogen bombs work. So atomic bombs do this, hydrogen bombs do this. That's why they're so much more powerful. And the sun is basically like a giant hydrogen bomb that's been blowing up for the last 5 billion years. But that's basically the source of nuclear energy. Now, there are hundreds of known isotopes out there. I forget, like maybe 400 isotopes. I'm not sure, but there's a lot of isotopes out there. And of all those isotopes, there's only 3 of them that actually could be used for nuclear fission. And here's why. It's not just that I need it to be able to be split. Okay, we call that fissionable. So like if a big nucleus that can be split by a neutron, we call it fissionable. But I also need it to release more neutrons. And one that does that we call fissile. So a fissile isotope is one that can be split with a neutron, and in that process will release more neutrons, which can then go on to split more atoms and establish a chain reaction. Now, it turns out there's really only 3 fissile isotopes known. Uranium-233, it occurs in very low abundance. Uranium-235, this is what we use for nuclear power. And there's plutonium-239, which doesn't occur naturally on Earth, but can be produced by neutron bombardment of uranium or other elements, and it has its problems that we'll talk about in a minute. But let's talk about a nuclear chain reaction. So the idea of a nuclear chain reaction is this. I'm going to send a neutron at a large nucleus, say uranium-235. Now, I should point out right now, the neutron speed matters. And so in nuclear power, we often have a thing called a moderator. It could be water or graphite, but basically it's going to slow the neutron down so it's going at the optimal speed to cause this baby to split. But when this splits, it splits in these two fission fragments or fission products, whichever you want to call them, and gives off usually three neutrons. And those neutrons fly out, and they might split other uranium nuclei, which will then give off neutrons and split other uranium nuclei. And so basically, if I get it right, I get a very rapidly accelerating chain reaction. Well, the trick with nuclear power, this is what we want to happen in a bomb. We want to have a rapid acceleration. But in a nuclear reactor, I want to control this so that I have just a very steady chain reaction rather than an uncontrolled chain reaction. But this still, it's all about the neutrons splitting the uranium-235 nuclei. Now, plutonium works. And there are countries that do use plutonium for nuclear power, and like the U.S. Navy uses plutonium for nuclear power. But the thing is, uh, it's very toxic. Apart from being radioactive, it's also toxic, and it's fairly easy to separate it chemically because it's a different chemical, so it can be chemically separated from other metals that might be combined with, and so and it's very easily processed therefore into nuclear weapons. So for that reason, we tend not to use plutonium. We could in the future if we needed to, but right now we tend not to, just mainly out of fear that it will get used for weapons production. So, as I said, uranium-235 is really the isotope that people use for nuclear power. Now, the thing is, if we go out we go out into the world and mine uranium out of the ground, what we'll find is that it's pretty much the same everywhere we go. For every 1,000 uranium atoms I pull out of the ground, about 3 of them happen to be uranium-235, and almost all the rest of them are uranium-238. Uranium-238 is fissionable. You can split it, but it's not fissile. It doesn't give off neutrons, so it's no good for making a chain reaction. You can't use uh, uh, uranium-238 for nuclear power. You've got it. Therefore, what you have to do is you have to enrich the uranium in uranium-235. You don't have to have pure uranium-235, not by a long shot. But you have to basically find a way of increasing the percentage of uranium-235. 0.3% won't work, but guess what? 3% does. So we've got to basically get a tenfold enrichment of it. And they do this with these centrifuges. If you've paid attention to the news, you might have heard that most countries in the world are concerned about Iran. Iran has a nuclear program. They say they're doing it to enrich the uranium in order to make nuclear power. But the same process by which you enrich things to make reactor grade uranium, which we call low enriched uranium, or LEU. Low enriched uranium is 3% uranium-235. It can be used in reactors, but it will never make a bomb. So it's worth noting you can never, ever, ever, ever have a nuclear power plant undergo a nuclear explosion because it's got low enriched uranium in it. It just simply is incapable. It could no more explode than your head could. All right. Highly enriched uranium, or HEU, that's what gets used in bombs. And for that, you've got to be 10 times more enriched than reactor grade. So 30% uranium-235, at least, maybe 50%, maybe more. The problem is the same process that gets you to here, you just do it 10 times longer, it gets you to here. That's why people aren't very happy with Iran right now. Okay, but let's just say I have the LEU now. I have that low enriched uranium. What I do is I fashion it into pellets. You might have heard the term yellow cake. So yellow cake is this uranium oxide is how it's usually processed and made into like a ceramic pellet. And the ceramic pellet is put in a titanium metal tube. We call that a fuel rod. All right. Now these fuel rods, when they're placed near each other, neutrons leaving one fuel rod pass through a moderator. Now that moderator is often water. It could be other things, liquid sodium, graphite, but basically it helps slow down that neutron to make it more likely to split another atom. It also serves to keep the reactor cool. But the idea is a neutron leaving one fuel rod passes through another fuel rod and splits a uranium atom there, a uranium-235 atom, and that gives off 3 neutrons, and those neutrons are going to go off in different directions, and then they'll split other atoms, which will send out neutrons. And the name of the game is to try to have a steady stream of fissioning events happening, and that energy then is given off as heat. I can use it to generate electricity. That's the idea behind it. I want to have a sustained, controllable chain reaction happening in these fuel rods. Well, how do you manage to do that? Well, to keep control, you need to have a thing called control rods. So control rods are not fuel rods, but they go in between the fuel rods, and basically they contain isotopes that are good at absorbing neutrons. So when you put these in, they basically dampen the reaction by absorbing the neutrons. So a neutron coming out of this atom here can't make it through the control rod, so it can't split these atoms over here. So the idea is if you want to control the fission process, you've got to control the neutrons. And the way you control the neutrons is by having these cadmium or boron or silver containing control rods that are good at absorbing neutrons. So this is just a diagram so you just see the idea. So if I put the green things here represent control rods, these larger ones here represent fuel rods. So when I put the control rods almost all the way in, you can see this shows a little bit warm because there's some neutrons getting through, but I'm blocking a lot of them. But then if I lift the control rods up, and yes, usually we lift them, the idea then is that more of the neutrons are finding their target, so it gets hotter. So if I want to control the heat of this reactor core, as we call it, where the fuel rods and control rods are, I do it by changing where these control rods are. So that's what nuclear power plant operators do. They control this, and they basically, the idea is when I have a reaction, when for every atom that splits, if one more atom gets split, so I have a 1-to-1 ratio of atoms being split and then making more atoms split, I call that a critical mass. If I have less than that, the reaction quickly stops. I call it being subcritical. And if it starts to become a runaway reaction where I start with one fissioning event and that leads to 2, which leads to 4, which leads to 8, which leads to 16. Now it's growing exponentially. I call that a supercritical mass, and we don't want that. Okay, that we quickly lose control. So the name of the game is to use these control rods to maintain a critical mass in our reactor core. And I guess that's what this slide was talking about. Sorry, I got talked ahead of myself a little bit there. Okay. Now, so the fuel rods and the control rods, which we see here, are kept together in a thing called the reactor vessel or the reactor core. This is where the action happens. This is where the heat is being given off. This is where nuclear potential energy is being converted into heat energy. And you know what? It's just like any other electrical generation system. We want to make steam in order to turn a turbine. But we're doing this in this case, instead of by burning coal, we're doing it by letting uranium react with other uranium atoms. So what we do here is this. We pump water through here, and as it goes through here, it heats up. Now I take this hot water as it goes through here, and it's going to go through a heat exchange because it's very important. In going through here, this water is likely to become radioactive, which is not a good thing. All right. And so what we do is we pass the water through a heat exchanger here, and then there's another body of water that comes through here, and it gets heated into steam. So basically, the water that circulates through the reactor vessel, the core, it does not come into contact with the water that's actually turning the turbine. All right, so they're kept separate, and usually this whole thing this constitutes the reactor core, and it's kept in a special room. Now, there's other ways of doing it. We're just going to talk about that one. So here's a bigger, crisper diagram. Okay, so here's my core. I'm going to pump water through here. As that radioactive water goes through here, it's going to make the water in this chamber boil. That water is going to come up here. And now I have high pressure steam to turn a turbine, which turns an electric generator, which makes electricity flow in the wires here. But now I've got to make sure that there's a pressure difference between here and here. So I've got to turn this back into liquid water. I do that by cooling it off by having a cooling tower. So these are kind of the emblematic symbols of nuclear power, although we use them with coal plants too. And the idea is I cool this water off. And really, the only thing that really comes out of the power plant that's bad is warm water. So thermal pollution is definitely a thing with these, but this is called a containment structure. So if anything was to go wrong, I have this large concrete containment structure that keeps this stuff from getting out into the wider environment. So let's just talk about what can go wrong. So if control rods are not inserted correctly, or if the flow of water or whatever fluid is carrying the heat out of the reactor core gets disrupted for some reason, what can happen is the temperature can get too hot. And if it gets hot enough that the control rods or the fuel rods begin to melt, we have a condition we call a meltdown. And the thing with a meltdown is basically we're no longer able to control the reaction. We can't insert these rods anymore, and so we've got this problem now. Here's what happens. Basically, it is not going to explode. It can't. It is not high enriched uranium. It often will. It's so hot it will melt through the bottom of the reactor vessel. So now we got this radioactive gook all over the floor. There's often a steam explosion associated with this because I basically melted this high pressure steam container. So there is an explosion, but it's a steam explosion. But it's inside, should be, if it's built correctly, inside a big concrete dome that could withstand having a jet aircraft wrecked into it. But now inside this containment structure, I've got a real mess. That's what happens in a meltdown. So they're not this amazingly catastrophic event they often get billed as. I'm not saying they're good, but I'm saying that they're not as catastrophic as most people seem to think. And it's happened 3 times, and we're going to look at each of these, okay? But again, one more time, you cannot have a nuclear explosion from a nuclear power plant because what it takes to make that happen is so highly orchestrated. And let's just start with the fact that we have the wrong kind of nuclear fuel. It is impossible for it to undergo a nuclear explosion. But it can melt down, and that's why it's really important to have this containment structure. This containment structure has a big, thick concrete floor. Is designed so if something goes wrong, and these fuel rods in your melt, they'll come out of they'll melt right through the bottom of this reactor core. They'll make a big white hot puddle on the floor for a little while, but they'll quickly go subcritical, and then it will release a bunch of steam, and that steam is going to be radioactive, and that's basically what happens in a meltdown. There have been 3 of them. Let's look at them in turn. First one happened near where Mr. Paul's from. Happened in a place called Harrisburg, Pennsylvania, at a place called 3 Mile Island. Now, basically, there was a water pump. I believe they were doing like a test, and something went wrong. And basically, they didn't pump water through it correctly, so it got so hot it melted down. Now, in this case, it did just like I said. Basically, this got so hot it melted through. There was a steam explosion. The steam explosion was contained. Some of the steam escaped into the environment, so there was some release of radioactive material into the environment, but most of it stayed within that containment structure. Now, here's the thing: it was this huge deal. It basically that almost single-handedly put an end to most nuclear power in the United States, and yet the death toll 0. And that's taking into account like all the health effects that might have happened. From people, years later from the exposure. We know a lot about radiation and the chances of your exposure giving you cancer. And World Health Organization goes, yeah, nobody died as a result of this. Then there's Chernobyl. Chernobyl is the by far the worst disaster that ever happened in a nuclear power plant. And this happened in what was the USSR, which is now Russia. Again, it was just like a routine system check, but it caused like basically a voltage surge and basically, whatever. So you got these bubbles started forming, and that let neutrons through too fast. The bottom line is you had a meltdown, and there was an explosion. But what they were using as a moderator instead of water, they were using graphite, which is a form of carbon. Well, carbon burns, so you got this fire that happened. So this fire basically was billowing up, and it about 5% of the reactor core material just ended up in the atmosphere, blowing all over the world, right? And this happened because the Russians were like, hey, why spend all this money on a containment structure? So it's like having a nuclear power plant in a Costco. There was basically, there was nothing to hold it back. Now, absolute disaster, right? Many workers died in a short period of time from exposure. Some died that night, okay? But check this out. So of all the people who got exposed in the world, especially people close by, World Health Organization looked into it and said, you know what? Probably grand total of people who died from this, 45 people. Now, I'm not saying it wasn't a terrible disaster, but I'm saying let's be realistic. 45 people died, and by the way, you can go there now. Okay, so people have this idea that nuclear power is this super devastating problem when it goes wrong, and I don't want to dismiss the I don't want to make light of the problems, but people overinflate the harm it does, and they underinflate the harm that natural gas, coal, and oil do. Okay, now let's talk about Fukushima. This is the most recent one. So what you had there was you had a earthquake that caused a tsunami. The tsunami was a pretty big tsunami too, came ashore, and it basically disrupted electricity at the plant. So the plant wasn't able to maintain their pumps, and then they got a meltdown. Now, what happened was, as the water drained out of it after because of the meltdown. So now you have the water in the reactor core is basically getting so hot is decomposing into hydrogen and oxygen. But there's a containment structure. But inside this containment structure, you're building up hydrogen. Hopefully, your chemistry teacher showed you what happens when you ignite hydrogen, but it explodes. Now, it's not a hydrogen bomb like an H bomb, but it's like a hydrogen explosion. And that explosion blew the lid off these reactors and released radioactive material into the countryside. All right. So, I mean, there was a significant amount of release, okay? But again, look at this. 1,500 people died, but none of them died from radiation. They died from panic. They died from car wrecks. They died from heart attacks. They died from being trampled. 1,500 people died because they were afraid of nuclear power. But how many people died because of exposure to radiation? The answer is 0 people died. And the reason I keep emphasizing this is, people, this is a known technology. This is not something that someday in the future could save us from global warming. It could save us from global warming today. It is expensive. Okay, that is the biggest drawback here. Okay, but just consider this for a second. Just please consider this. World Health Organization has no skin in the game, right? They're not making money off this. They have ways of trying to determine how many people die. What they say is the total number of people who've died from nuclear accidents is 45 people died because of Chernobyl, period, in the entire time that people have been using nuclear power. But every year, almost 1 million people die from complications caused by air pollution from coal exhaust and car exhaust. But nobody cares about that. Nobody turns a TV camera on that. But it's killing so many people, and we're going to run out of this. And if we don't come up with a backup plan before we run out of it, it's going to lead to not just an environmental catastrophe, but also an economic catastrophe that could precipitate the end of society. All right, we have a way out of it. It's called nuclear power. If we would simply get over our fear and move on with it. So, nuclear power is clean technology. All right. The only thing that comes out of it is some steam and some thermal pollution of waterways. But there's no other effluent from it. We're not putting anything in the atmosphere. Imagine Korea with blue skies like this every day. We could have this. Switch to nuclear power. This is what you get. All right. You have to deal with the fact that there could be an accident, but that accident is unlikely to cause you harm. Now, what are the biggest problems then? There's 2 big problems, and there's no getting around this. First is they are hugely expensive because if you build them correctly, not the Chernobyl way, but the correct way, like the 3 Mile Island way, you have to have good containment structures. But over their lifetime, they actually produce electricity for less money per joule than what it costs to generate at a coal plant. So it's basically you're putting the money up front, but in the long run, you're getting money out of it. The biggest problem right now is spent fuel rods, and we'll talk about this in our next screencast. But the bottom line is, after fuel rods are done and control rods, they had to be stored somewhere basically forever because they're super radioactive. It's not that they'll get out into the environment, but they still have to be managed forever. And this is a real problem that there is a way around, but for right now, we're not using any method of dealing with that. So sorry this one was so long. Obviously, I'm impassioned about it. I really worry about the future of the world. I see a path forward, and people won't take it out of fear. All right, so let me